Hello, everybody. As I indicated last week, I am pre-recording my pre-lab lecture so that you will have the entire lab period to do it. My experience with other classes is that this is one of our longer labs, so really make sure that you come in prepared to just start executing the actual lab itself. So this lab this skill set is called Colorimetric Assays. It is actually composed of two different assays that you will be working on. One is a BCA assay, and the second is the activity assay. And I'll go into a little bit more as to what these assays are, how they work, and some of the analysis behind it. So, kind of from an overview, we have the enzyme kinetic assay. And what this is measuring is your enzyme activity as a function of time. So you will be looking at a reaction as it is occurring and measuring that reaction over time. It will require the use of Beer's law, and we'll get into that. And we'll also talk about the right amount of enzyme activity. If you put too much enzyme in, it's going to be too fast of a reaction for you to be able to measure. If you put too little in, you'll see that it really is in the noise of the equipment. The second, and I'm horrible at pronouncing this, I'll just call it the BCA assay. This is an assay that measures protein content. It is a single point, and in our next slide, we'll talk about the difference between a static or time point and more of a reaction over time type assay and how we measure it. It is used to determine protein concentration. So powerful assay that way. The caveat, and I'll mention it again, is that it really doesn't measure a specific protein, but it measures all the protein that you would have in a sample. So great assay for measuring protein concentration, but not specific. The enzyme kinetic assay, the first one that I mentioned up here, that one is specific to a protein. We won't be using the protein that we'll be using in Project 1 today, but as we move into Project 1, note that it will be specific to the LDH that we will be using. It does determine the protein concentration, but in order to do that, it requires a standard curve. And again, the standard curve is using the principles of Beer's law. So Beer's law is used in both of them in quite a different way. So I have moved this skills lab to the very end of our skills lab set because it is so important for the upcoming projects. These two assays are going to be the workhorse for you as we go through purification to be measuring the purity of our product that we go through, that we're purifying, along with the amount. So it's the quality and the quantity of the protein that you will be purifying that these assays measure. Very, very important assays. So take your time today to work your way through them, understand them, so when we hit Project 1, they will make a lot more sense. So let's talk about the difference between a kinetic versus an endpoint assay. So our activity assay is a kinetic assay. Our BCA assay is an endpoint assay. So when we think about kinetic, we think about movement. And what your activity assay is doing, it is a kinetic measurement. It's recording the reaction over time. I indicated it's using Beer's law. Beer's law looks at the relationship of absorbance versus concentration when we did it in Chem 122 and 250. And this time, we're going to be looking at absorbance versus time and looking at the rate of change of absorbance versus time. And you'll see that as we move forward. Again, that time variable indicates that it is a kinetic measurement type assay. The second assay, the BCA, is an endpoint assay. What do we mean by that? It means we still have a reaction going on, but we're going to measure the reaction at one time point. So the reaction could be occurring before it, it'll occur after it, but we're measuring it at a single time point. So, with that said, you will have a lot of different measurements to take. Speed of taking your final endpoint measurement is critical for the BCA. So kinetic, you will be measuring absorbance versus time as the measurement. In the BCA assay, you'll be taking a single time point and measuring that. That time point with perspective of your other samples is again critical. So you want to make sure that you're set up to run these all at once in a single setting over a small period of time. So hopefully that makes sense. Both of them, the activity assay and the BCA assay, are reactions type assay. The difference is the activity assay, you're measuring the reaction over time. The BCA assay, you're measuring that reaction at a single time point. So let's go a little bit deeper into the kinetic, enzyme kinetic assay. What you're again measuring is enzyme activity. Enzyme is an equivalent term to a catalyst. So an enzyme catalyzes a biochemical reaction. What we will be measuring is the initial rate of product production. So as I said in the last slide, your enzyme activity is measuring absorbance versus time. And what you see here is what you will typically see as you're measuring your enzyme activity. You have your absorbance on the y-axis, time on the x, and you can see the rate of change of this reaction going on. We are measuring the initial rate of change of when the reactants are going to products. And as you can see here, you have an initial straight line, if I drew it right here, and then it starts leveling off. And this is very typical of an enzyme, of a kinetic assay, or in this case, our activity assay. What you will be measuring is only this initial rate of change. And this initial rate of change is where the reactants are fully going to product. You don't have the reverse reaction of product going to reaction going on at that initially due to Le Chatelier's principle. So the rate of change of product over time, where what we're measuring is the concentration of the product. We start at the end point where time, your product is equal to 0 and time is equal to 0, and measure the initial one. In an activity assay, we express our units as units. And it's an international convention that we use. And so 1 unit is equal to 1 micromole per minute. So as you go through your analysis of this, you will be converting from your absorbance versus time into micromoles per minute. I have 2 different pictures here, and they show 2 different considerations you need as you analyze your assay. If your concentration is too high, you're going to have a very sharp initial rate of reaction, and it's going to steep off or peak off extremely fast. that means you have too concentrated of an enzyme in there. And a lot of times it will be so fast by the time you get measurement, you'll just see this peaking of it up here. The second is if your enzyme concentration is too low, and this is the type of thing that you see when it's too low, and you start getting into the noise of your measurement. So in an ideal concentration, you want to have the initial rate being such that you can draw a nice straight line through it. This has a little bit too high of a concentration. You want this initial slope a little bit longer. This concentration is too low. If you have too high of a concentration, that's an easy problem to fix. You dilute your sample and you compensate for it. If your concentration is too low, that's a little bit harder in order to correct unless you have already diluted your sample in there. So that's the kinetic assay, and what you will be seeing as after you take your initial readings and you move them into the analysis to be able to determine your enzyme activity. Again, we'll go into the actual equations that you'll be using, but you want this you will be plotting your reaction over time, and the measurement that you'll be taking on your spectrometer will be time-based measurements. You'll take them every second as you watch the reaction going on. The reaction that we're looking at today is a beta-galactase activity assay. When we do project 1, you will be using your specific protein, LDH, for this activity assay. So what's happening? What beta-galactase does is in a cell it hydrolyzes your polysaccharides into monosaccharides. So in a cell, you go from your polysaccharides, you use beta-galactase is used as an enzyme, and it converts that into monosaccharides. That's what's happening in the cell. In our cuvette, or in our reaction that we're working with today, we're actually taking, and again, horrible pronunciation, you're taking your orthonitrophenol beta-galactide into galactase. And it is being catalyzed by your beta-galactase. In this reaction, as beta-galactase converts it to the ONP and the galactase, your ONP can be measured. And that is what we are measuring, is the rate of production of ONP over time. And the maximum wavelength that it can be measured at is 420. And you'll see a slight yellow going on in your cuvette. So today's activity assay, we are measuring the production of the ONP being catalyzed by your beta-galactase. In the measurement, so you will be putting it in a spectrometer, you will be measuring time and the absorbance of the ONP over time. When you take that data out of the spectrometer, you can plot it and it will look something like this. It won't be at 612, it'll be at 420. It will be at 420, but you'll get something like this as a measurement. What you will want to do, actually I'm in the wrong slide here and I'm going the wrong direction. But again, I have the same slide I was looking for. What you are going to do is measure this slope. And again, you don't see the slope over the full set of data. And that's an extremely important thing to consider as you're analyzing your data. You just want the initial portion. So notice this slope is not going from 0 to 250. It's just measuring it, looks like from 0 to 100 here. This slope as you convert it becomes the rate of change of concentration over time. And that's using Beer's law. What you will need is the extinction coefficient. And in this case, the extinction coefficient is 18,000, inverse molarity and inverse centimeters. And the length of that your light will travel is 1 centimeter. And finally, you will need to convert it into units per milliliter. Again, that units is micromoles per minute. When you come into lab on Tuesday, I will give you a cheat sheet to help you with your analysis of your activity assay data. So this is one analysis that students tend to struggle with. Key points here, again, get your slope, and you want the slope only of the initial portion. If you are taking the slope directly off the trend line, another important consideration is to make sure you get enough significant figures. A lot of times the slope is very, very small, and what the trend line will give you is only 1 significant figure. This has too many on here. I would use the first 3 or 4, but you want at least 3 significant figures in order to carry that forward to do your actual analysis with. You will be using the slope of that initial portion along with the extinction coefficient, the length of that the path has to go through, along with a set of conversions in order to get you in the right units to be able to publish your data. And that units will be in units per milliliter. And again, if I forget to hand it out, I do have a cheat sheet to help you with these calculations that you'll be using. The activity assay is what you will be using over and over in both Project 1 and Project 2. Take time in this project to understand the assay and to be able to quickly go through the analysis of it. So take time to learn how to set it up. There's some tips setting up and organizing your Excel spreadsheets for this activity assay will help you in the long run as you go through the next set of projects. Let's now talk about the BCA assay. As I mentioned earlier, this is a protein assay. It measures your protein, how much protein you have in it. A key thing to know about this is it is not specific to a protein. Your activity assay, since your Project 1 using LDH is an enzyme, we're going to be measuring just the reaction that enzyme is catalyzing. So it's very specific to our protein for Project 1 and 2. The BCA assay is not protein specific. There's a lot of other different assays out there. I was used to the Bradford when I was in industry. Again, what you use depends on the type of chemistry that you have and your compatibility with your different reagents. The important thing with a BCA assay is it requires a standard curve. Standard curve like you've produced and all of your Beer's laws experience prior to this lab. In the standard curve, since this is a time point assay, and to take us back and remind us what that means, or an endpoint assay, we are taking a reaction as it goes and measuring it at a set point in time. That set point in time varies depending on the conditions, the temperature, the time that you've waited for it to measure. Because of that, every time you run a BCA assay, you need to generate a standard curve. So what we tend to do is hold all of our samples so that we can run them all at once. Think about it. If you need create a standard curve each time you only have one sample to measure, then it's not very efficient. You tend to hold all your samples or a group of samples, run your standard curve, and then run all of your samples at once. In the case of today's assay, BCA assay, and when we do project 1, your standard curve will be based on BSA. And we'll go a little bit into that. Oops, going the wrong way again. What the BCA is measuring, it is a copper reduction assay going on. So the copper is reduced by a peptide bond. So the peptide bond reduces the, I said it inverse of what I really meant. I guess it's too early for this. The peptide bond reduces the copper. Copper from C2 plus to C plus. And the amount of your copper 2 plus is dependent on the amount of protein, or the amount that it's reduced is a function of the amount of protein that you have in your sample. So for 2 BCA molecules, they cleate a copper plus ion in there. What you will see with your sample is purple forming. I think it's a beautiful assay in that standpoint. The amount of purple is proportional to the amount of copper plus ion that's produced from step 1. And that is a function, again, of the amount of protein. So the more protein that you have, the more purple that you'll see as the reaction goes on. And as you produce the samples that you'll need for your standard curve, you'll see what you will visually see is a gradient of purple. You'll go from light purple to dark purple because your concentration of protein to create that curve is increasing. Beautiful assay from that standpoint. As I've said, a new standard curve is required for each time you run an assay. In this case, we're running what you can consider a standard Beer's law that you've seen before type curve, where you are plotting concentration on the x-axis and absorbance on the y. So each protein has a slightly different response or sensitivity to this assay. That's one reason why we run a standard curve each time. The other is the time function. After you've created your standard curve, and you will be creating a BSA standard curve for this lab period along with when we run project 1. Once you've created this standard curve, then you can use it to measure all your unknown sample concentrations. So again, pretty basic from what we do in this case. After you have your standard curve, all of your samples, you'll measure the absorbance. You'll use the trend line information to take your absorbance from your sample to determine the protein concentration of that sample. We'll be using the best fit line in this case for the measurement. So this should look fairly familiar to you. We've used this Beer's law type assay in most of our Gen Chem that we've done. I know I'm teaching Chem 251 right now. We're using and creating a Beer's law type calibration curve this week also. So good Beer's law week for me. So that's the end of my background that you need for this lab period. Again, go through the lab manual. read and prep for this lab period. It will take you all of the lab in order to do your BCA assay. It's a reaction-based assay. You will be putting your samples into an oven or a water bath. They need to be at 40 degrees for about a half an hour in order to do it. So there is a time piece in there. The standard curve, you will need to set up your dilutions for it. So again, that will take time. I would start with the BCA assay to get your samples prepped, to get them in the oven in order to be able to get ready to measure. The measurement is very time critical. I think I've said that about 4 times for your BCA. So after that wait period, make sure that you have your spectrometer set up so that you can immediately take those samples. After you've got your BCA set up, dilutions made, all of your unknowns prepped, and in the oven, I would start to set up for your activity assay. I don't recommend trying to start performing your activity assay in that 30-minute period. Just get everything really well set up because you want to be nice and relaxed when you pull the BCA out to be able to do those measurements. You will be doing replicate measurements. The idea behind the replicate for our standard curve is to understand outliers and to be able to remove any of those outliers and also get a nice average in there. When you start running the activity assay, it is time critical in getting the sample into the spectrometer. So get everything prepped, and it is your last aliquot where you're putting your last ingredient into your cuvette. That time to get it from when you put it in there to getting into the cuvette or getting it into the spectrometer to measure is extremely critical so you can get that initial rate. The analysis for this will take time, and so set aside time between a class period and when the lab is due. The time that you put in now will really help you with later and the time when you start performing Project 1. Project 1 starts next week, so you will have a break in doing post labs, but come in prepared to start performing Project Run right away. Starting next week, it will be a 6-week project, and then after that, we will move into Project 2. So hopefully that was good background, and I will see you in class on Thursday.